Okay, I'm just gonna record this, but honestly, um, it's better to just look at the playlist. Someone asked me, is the exam online or open notes? The exam is not open notes and it is online, but you'll be like online, but like in person, you know? Like you'll just open up Canvas. We'll give you the password in your section. So go to your section. Kind of how you've been doing the quizzes. It's kind of like the quiz format. Okay, any other questions in regards to like the test or the format? Is it due at the end of the class? Yes, it is due at the end of the class. How many? What isn't on the test? Well, a lot of things aren't on the test. I don't know how to answer that question, Mia. How many MCQs? Like major topics? Well, the thing is, I actually haven't been sitting in with y'all's classes, so I don't know what you guys been learning / not. Oh, postfix is not on this test. I can tell you that. I know you just learned that. Let me check how many questions there are. If you give me a moment. I think there's like something like 50. Hold up. I can check for y'all. Maybe. I think it was kind of like 50 or something like that. Basically, you have to go pretty fast. But you guys are gonna do great. Let's see. Okay, well, maybe not. Maybe it's not 50. I'm sorry. No, don't freak out. I don't know if any of the peer teachers remember how many questions they had.
I think it's 30 multiple choice and 2 FRQ. At least that's kind of what it was for us.
Okay, well, the test hasn't changed, so go with that.
Okay, yeah, so 30 multiple choice and 2 FRQ in 50 minutes.
Okay, yes, thank you, Andrew. Okay. Yes, not 50. Okay, any other questions in regards to test formatting? Free response questions is what FRQ stands for. Is there a proactive exam? So yeah, there's only like one coding thing. The second one is kind of like, the second one is still free response, but it's on like hard code coding. Is there a practice exam? No, I guess your study guide. There is no practice exam, from my understanding. Will you able to review our quizzes? Are they not open yet? Can you guys see your quizzes? Okay. Oh, okay. Wonderful. If you can't, tell one of the TAs or better yet, Dr. Lake. Oh, we can, but not what is wrong. Oh. Okay, I'll ask. Let me make myself a note. I'm not sure. Are students supposed to... Okay, I'll ask about that. Does code have to work on it or can it be okay? This is kind of how the rubric works. Make sure your code compiles, even if it's like kind of wrong. Wait, okay, hold on. Let me see if I still have the rubric from last semester, and then I'll tell you what to look out for. Let's see, rubric. Ba-da-bum. Maybe I don't have it. I was 2022. Let's see. Okay. Okay. Let me give you some like little hints from the free response questions. Oh. wherever you can impartial if they understand what you're trying to do. So comment. Yes. Oma makes a great point. Okay. I'm reading the rubric right now. Make sure if we tell you not to do something, to not do it, because or else we can't award you any points, even if it works. So let's say you're working with iterators and it tells you not to use brackets. Do not use brackets, please. Because that's a lot of points that we have to take off. Pseudocode definitely works. Make sure your code compiles. Is it being make sure your code compiles in regards to just make sure it compiles. Even if everything's wrong, like comment out your wrong code and make sure to just like write your pseudocode in comments, like what you would have done. But that when you run g++ main.cpp, make sure it compiles, because in the past, the rubrics have included, does the code compile? Will we to use? Yes, you can use VS Code when you write the code. Are we allowed to use Note? It's not OpenNote. I think you can, you may be able to use your PA though. I'm not sure about that one. Are we allowed to use notes? Okay, yes, you do have to study non-comparison sorting. No, you cannot use passcode. Okay, yes, so VS Code, no passcode. And how do we know what the correct, okay, the correct answers to the quizzes? I'm gonna ask about that. I'm not really sure about that. But if, just come to office hours or compare with a friend or something. Okay. Okay, well, now that that's done, I'm gonna send out this Google form. And it's basically gonna ask you guys, you know what, just fill it out. Okay, I sent out a Google form in the chat. Please fill it out. It will help us know what topics we want to see first. You have 2 for responses. Yes, thank you to the peer teachers answering questions. Yes. Oh, 2 responses. Oh. Yes. I'll give you like 2 minutes for everyone to please respond to that Google form. Okay, so far we have 27 responses. There are 62 of you. So you should, there we go. Ooh, this is a good question while I wait for everyone to respond. When to and when not to use std move. from PA demo. Oh, I don't know what the PA1 demo said. You'll basically want to use std move whenever you want to steal something, and it's never going to be used again. Let me look at the PA demo. I'll answer that question better in a few minutes. Is the best way? Someone asked, cover all topics listed. That's what the YouTube playlist is for. So don't you worry. What can be put to? Okay. I have 45 responses. I'm gonna. Okay, so 44% of you guys, which is the majority, wants to go over pointers and arithmetic, references, arrays, and iterators. So.
Okay. Should I just share the slides for that and talk about them, Sophia? Or?
Yeah, you should, but like, make sure to like what specifically are you guys confused about? Like, put that in the chat.
Yeah, because I can talk about a lot of stuff. If I don't get anything, I'll just have to do what I already did in the recording, which is just the entire set of slides.
Yeah. So everyone drop in the chat what you guys are confused about. What we need to do on the test. Oh, so you're talking about like the first or your free response question and stuff? Or are you asking about multiple choice questions? Oh. Well, if you want to see the whole thing, you should definitely look at the video. Okay, we got pointer. Okay, well, we can't give you the answers to the free response. Activating amortized runtime iterator.
You said like a large amount of people wanted to do my topic, right?
Yeah.
I could just go over what I think is probably the most important from it if no one has any specific iterators. Okay. I'll just share my slides, I think.
Yeah, and feel free if you want to do like some examples, live coding session, you can. If not, that's fine.
Okay, I can't share my yeah.
Oh, sorry.
I can't share my okay.
Okay, there you go.
All right. Share screen. Okay. And these slides, well, I don't know if these slides are necessarily available, but you can see them all in the video. There's a playlist. Let me start at the most important.
Yeah, the slides are linked in the comments. So in the comment of the video, I can give you.
Okay, people are saying, I guess, iterators. Okay, I'm gonna go through iterators, then I'll probably do pointer arithmetic. So iterators down here. Okay, yeah, so to go through iterators, I kind of describe them as just fancy pointers. So let me see. Yeah, so when I say a fancy pointer, I mean, don't be afraid of iterators or what they do. It's just going to be a pointer, but you can use it for a lot more things. I don't have like too many specific examples for the test. I think Sophia will have access to stuff kind of like that more so than me. But I'd say the general points you should know are kind of what they look like in comparison to your PA1. And you should know these two bottom points very well, right? The fast create and copy. And also what we used in PA1 were considered random access iterators. And under that, we know we can move forward and backwards. And in your insert or erase or whatever function, you might have used iter minus minus as your loop conditions. Like kind of over here, I have these. This is just a basic one. And I have another, yeah, okay. Your vector grow slide, this is really important, okay? When we have our grow function, like in PA1 here, right? Once we make an iterator to our vector, like right here, I have auto iter equals vector dot begin. If we call grow, or more importantly, if it just gets called, you know, maybe we resize the array or we do push back, probably, the iterator that once was pointing to vector dot begin is invalidated. So I made it like bold. I basically made everything I could make it because the word is very important. You should remember that when grow happens on your vector function, the any iterators are then invalidated, right? Because we resize it and the pointers change when we make the new array right here, where we say t, reference operator new array. Yeah, because when you make a new array and you resize it, everything's going to change. I don't know if anyone has any other specific. Why is it called random access? I guess I could Google that. I mean, Sophia, do you know why it's called a random access iterator?
No, I just know it is.
I mean, yeah, I just know it is. That's probably not something you should worry about. Why is it called random access? I don't know. I think more importantly, you should understand that it's a bidirectional iterator in PA1. Didn't see the link to download the slides. Okay. Do we have a bunch of practice questions about pointers, refs, arrays, iterators? Yeah, I actually made some here, and there's more in other slides that someone could probably link later, but I have some good ones for pointer arithmetic that I can kind of talk about now. Okay, I kind of have this chat box. All right, yeah, so pointer arithmetic, I gave kind of a bunch of examples here. You could probably follow through with the video because it kind of pulls up these question marks here are kind of examples of what happens when you make your array called grades here. Ints, grades, new ints. So we know grades. Oh, it's also important that when you make an array, whatever size it is, this variable, this pointer, we know that that points to the first element, right? So right here, we have grades 0 is 78. That's what grades would be when we first call this. So if we dereference it, it's always going to be 78. And if we use pointer plus plus or grades plus plus, it'll then point to 88. So yeah, when we talk about this, I'm just going to kind of, I guess I could explain. Begin is a random iter and 1 is an int. I don't know what that's referring to. Anyways, yeah, there's answers to these in the video. I don't want to be like redundant and just repeat them. But what was the question exactly? Actually, let me look at it. Yeah, there's Sophia, they're like good slides and practice problems for pointer arithmetic. There's probably some in like their old quizzes, but I guess they can't see those.
I think they can see their old quizzes, but also you have Google. So just look pointer arithmetic practice, or my favorite method and how I learned these, especially when putting these slides together like last semester, is literally just go open a main.cpp, create an array, and then just go for it. Oh, see, Angie was doing that too.
Yeah, I have one, and then I think I have another. I don't know where it is. I don't know how to use this.
I know, you're good.
Variables.
Like, honestly, that's the best way to learn. Like, we can give you practice all day, but like you doing it yourself, I think. Not only will it give you good practice for the multiple choice questions, but also for your response.
Yeah, and I think Replit, I just use that, or online GDB, VS Code, whatever. You kind of play around in main and just start messing with stuff. Stuff like this, you can kind of just see what everything is. So these actually were specific examples in the slides over here. But you can kind of play around and see what happens when you mess with pointers and use pointer arithmetic. And so that's kind of your practice. I don't have any like specific questions other than these, which are in the slides that the link has been posted in the chat for. This is something I think is really important for the test I want to talk about. Okay, so there's obviously these questions, right? But a good example is this one right here, where we say hippo pointer array is equal to a new, so on the heap, array of hippos. I guess that's our class type here, and size 4. If we do then after this line, so this line and then this second line below it, array plus plus, if I ask you how much that pointer array is incremented by, like for a specific value, right? Because when we use pointer 1 to some array of integers like this, and we do like pointer 1 plus plus, we know it goes to 88, but there's a specific value that you can find when you type array plus plus. such that if you were to do, instead of array plus that value, it would move it to 88. So that's what this question is asking. And I'll go ahead and explain the answer to it right now. And basically there's a built-in function in C++ called size of, and then you pass in the type. The reason I didn't just use an integer here is to show that this works for whatever class we're speaking of. So in this case, it's a Hippo class, not a primitive type in C++, but if we type in size of here, we get the byte size for a Hippo. And if we were to type array plus that, it would essentially move it to the next element, just like array plus does. So the answer to this would be size of. And you should definitely remember that one, I'd say, for your test. Trying to see, does anyone have any specific questions about pointers, references? I'm going to try to, while I wait, I'm going to try to find this other example thing I have. Here's one. It's got good examples here. I've kind of just got some examples. This all corresponds to the code though. And Sophia, I don't know if there's any specific questions that you're getting from the survey that I can answer, but until then, I'm just basically repeating what's already on the slides for them. So
Let me check real quick for you.
okay, yeah, Mia. So you said is for something like pointer plus plus. So does array, okay, I'm gonna answer Mia first. So you said dereference pointer plus plus. So this example right here, is there an order of operations for which comes first? So the answer is yes. And what it's going to do is it's going to, what C++ sees is sees this dereference operator. It says, okay, I want to find the value, and it wants to find the value of pointer plus plus. And our pointer name in this case is grades. So our grade starts at 78 and we say dereference. So now it's searching for our value, right? It's searching for the value of grades plus plus. But in this line, the value of grades plus plus is not 88 yet. It's still 78. But then after this line runs, it will push it over to 88, which we can see in the line below, right? We have moved the pointer forward because we can then see out it. Like if I were to see out this before, just like this, it would be 78 still. So I hope that kind of helps. So does array plus plus equal array plus size of Hippo? Yes. Let me look at that. Where was that? Yeah, so right here, if we have our array code, I guess I can just kind of test that. This is a good example of what we mean when we say just test it, right? Open whatever. Let me look for it. Okay, C++ test. So yeah, I actually have an example right here. So imagine this pointer one array is your this right here, it's 78. Let's say our pointer one currently points to, I'll get rid of all this. Oh, I can't get rid of all that. And I don't know if you guys can see all this text very well. Do I need to zoom in at all? I think it's probably fine.
I think it's fine, but I don't know how the others feel.
Okay, cool. Yeah, so the size of an integer in this case pushes it forward size 4. How much is it? Sophia, there's a question I kind of have about this. You had mentioned this example specifically. When we do array plus plus, in this case, your argument's that if, say this is like, these are integers, right? But if I just did, like this was just int. This is new int. Array plus plus, is that going to do the equivalent of, is that going to do the equivalent of array plus equals size of int?
Not okay, so size of int is going to give you like an actual number. The reason I'm not sure that would work is because it's kind of being, it's like operation overload, so the plus sign is overloaded. something you need
Right.
to like something you need to understand is that in like binary, like all this C++ code is basically converted into binary at the very end. So let's say you have like an integer, right? An integer, to store an integer, it takes a certain amount of binary. That's why there's like an integer max, and you can like overflow with integers. But let's say, so when you do array plus plus, your compiler already knows exactly how many like bits, so how many like zeros and ones it takes to store an integer. And I think it's going to be like, I don't know the exact one, but let's say it's like 12. It takes 12 zeros and ones to store an integer. So it's just going to increase it by that 12 each time, right? But let's say we have an actual like hippo class. Well, the hippo class is it's gonna need more than like 8 binaries, 8 bits in order to increment itself. Like if you go increase it by 8, like you try to do with the integer, you may just land like halfway through the hippo class, and that's not good. So what the size of does is it basically goes and finds out how many bits it takes to store an entire hippo class. So then it just moves the entire array forward by that much. So this means that like your pointer, because your pointer is pointing at memory, right? Your pointer, by doing plus plus, it's incrementing by how much it's being stored, like how many bits it takes to store that type. Does that make sense?
Yeah, I think to add on to that kind of makes sense. We know that array plus plus, because if you guys remember in your PA1, you made for iterators and for we did operator overload for plus plus. We know what that does, right? But this array plus plus, it's kind of like that in the sense that this operator already knows how much it needs to move forward for, say, an integer, or in this case, a hippo, right? But I guess that is kind of synonymous to array plus, well, it's an interesting question. Plus equals size of.
I think technically array plus plus is equal to array plus size of hippo. I don't know, because the operation is being overloaded, size of hippo is going to give you like the number of like bits, so like 5. So because the operation is already overloaded, it's actually just going to
Oh,
increment the array up 5 indexes, but technically that is correct. Your compiler just has its
yeah.
operation overloaded.
So right here, it's kind of confusing because I say that it would be equal, which we have here, right? If we start at 78 and we do size of int, you would think that would just do the same as you think it would do the same as okay, this is set at 2 indents, and that's awful. I don't know why it keeps doing that to me. Anyways, my point is that if you do plus plus, it'll move it. But in this case, if you do plus size of int, it's 4. But that's because in the overload, it knows, right, that it's supposed to only move 1. So perhaps it's something about the actual size of the array in this case. But as you said, the answer is still going to be, like I have in the next slide, size of hippo. So I think it's fair to assume that the answer to your question is yes.
Yes. Okay. Any other questions on this iterators? If not, we will move on to non-comparison sorting, which is the next slide, the next big chunk. Let me check. No questions? Okay, we shall move on. Let me make sure I close all the tests things I have open, because that would be very bad. I know. Okay, yes, I think. Oh, let's just close all that. Oh, wow, I had so many things open. Okay, we should be good. And I shall share my screen. Okay, non-comparison based sorting versus base. There will be a video on this. I actually have not reviewed non-comparison based sorting in a bit, so this will be fun. Okay, there's like three we're gonna talk about. There's like bucket sort, and then there's counting sort, and then there's also radix sort. That's like the three you need to know. Bucket sort, it's a pretty straightforward. And it creates n buckets of even ranges, kind of like a histogram kind of thing. It runs in O of n times, but for this to like work, the elements need to be like evenly distributed. And if it's not evenly distributed, it will be O of n squared. So ideally, if all of the elements are good, it's O of n. Non-ideally, it's O of n squared. So let's take a look. We're going to create step 1, create n buckets with even ranges. So again, it's kind of like a histogram. Step 2, you're going to put each element from the original array into the appropriate bucket. So let's take this 87. Again, 87 goes into that bucket. Easy enough. Then you go 34, 34 goes in 30 to 39. And then you just like, I won't drag you through the pain of seeing each one being put. But in the end, you understand. You put the elements where they should go. The step 3 is to sort each bucket. And it's usually with insertion sort for some reason. I'm not really quite sure why. But as you notice, like, let's take this 34, 32, 36. You're just going to sort that. Boom. That's bucket sort. The next step is that you're going to start with the first bucket, and then you're just going to put the buckets together in a new sorted array. So like you just go down the line. So that's 8, 12, 32, 34, 36, 45, 53, you just go down the line and combine them all over again. Because of this, it now makes sense if they're evenly distributed, it'll only take O of n times, versus if it's not evenly distributed, it'll just take O of n squared. Because in that case, if you're using insertion sort, this will just be like one long line, and you're just basically sorting one array. So yes, if evenly distributed, it'll be O of n. If not, it's O of n squared. Bucket sort. Okay, counting sort. Oh wait, there's a question. Is bucket sort stable? That is a great question. It depends on the implementation. You could do this in both ways, technically. Yeah, honestly, it depends on the implementation. Like, you could implement it in a stable way versus you could implement it in a non-stable way. I think in the test, if it asks, you have to put stable. But I'll go check for you guys later. Counting sort. Counting sort, it uses 2 extra arrays. Yes. One is for counting, and one is for holding the sorted solution. And it runs in O of n plus k times. Do we know how it works? Oh yes, for these, you only have to know how it works. You don't have to code it. Or maybe if we give you, like, let's say we give you like bucket sort or counting sort or radix sort, and we give you the code, would you be able to tell if that code is stably sorting or not stably sorted? So yes, there's 2 arrays. One is for counting and one is for holding the sorted solution. It runs of O n plus k, where n is the number of elements, is k is the range of elements. So let's take this example. First, you want to define the range to set counting array. The range could be defined as 0 to 8, so with k equals 9. So what you kind of want to do is you kind of want to count like each like individual number. So notice how there's a 0. Like, you notice how the minimum is a 0 and the maximum is an 8. So in that case, you go 0, 1, 2, 3, 4, 5, 6, 7, 8. So you just want one index value per like unique number that there is. Notice how we still included 1, even though 1 is not in this list. Like, we just include it. Next, we basically just count the frequencies. So we notice that 0 appears 1 time, 2 appears 2 times, 2 appears 2 times, 3 appears 1 time, so on and so forth. Next, we're going to add the counts up as a cumulative sum. So if you observe, it's kind of like the reduce function, if you know what that is. But like we notice here, it's 0 plus 0 is 1. 1 plus 2 is 3. 3 plus 1 is 4. 4 plus so on and so forth. So you kind of follow these slides. Afterwards, you set up the array of the same size as the original array, which in the end, this will have the sorted solution. So starting from the end of the original array, we check what number it is, and we get the value of that index in the counting array, decrease the value by 1, and that is the index of the original array item will we place in the sorted array. So let's go through this one by one. We start at the end, we check what number it is, okay, we check it's 8, yes, and then we get the value of the index in the counting array. So we get the 7, and we decrease that by 1, and that is the index of the original array item. So boom. And we place that there. Do you see how we went from 7, we decreased that, and we know that the number 8 has to be in index 8. Boom. We're gonna do the exact same thing now with 5. We decrease that, and now this goes in 4. And you just go down, so on and so forth. Geeks for Geeks has a great video animation, so just look up counting sort Geeks for Geeks and just watch that a few times, and I think you'll get it intuitively. The important things I would mention about counting sort is that, like, let's say you're given a list of numbers, like just this array, and you're asked how much like the auxiliary array or like the frequency array has to be. Well, in this case, you know it has to be 9 because you start, the minimum is 0 and the maximum is 8. So you go, if you count 0, 1, 2, 3, 4, 5, 6, 7, 8, that's 9. Does that make sense to everyone? I know that was a lot. What is it? Is there any reason for starting at the end of the array? I'm not quite sure if there's a reason for starting at the end of the array. I mean, I'm sure there is, but I just know that's how the algorithm is. If 2 of the same data appear in different order in sorted array, it's unstable sort. Yes, Mia is correct in regards to when it is unstable. If 2 of the same, yes. Do we start from the end so that it's stable? Oh, that's a great question. I'm actually not sure. I will get back to you on that. Bum, ba-dum, bum. Okay. Next is radix sort. Radix sort uses counting sort to sort. I shall repeat this. Radix sort uses counting sort to sort. What an interesting fact. Okay. Remember that great for numbers if it's like this is a radix sort is great if k is smaller than n, and the runtime is n times k, where n is the number of elements and k is the maximum number of digits the elements has. So mistake caught during this array pointed by is the there's a mistake. Hold up. These are old slides, guys. Bear with me. This array pointed by is the array we are going to sort. Okay, yes. Oh, don't worry about that. Okay, we're gonna sort the elements by ones place digits. So notice how, well, you can see you first start sorting like the ones, and then you make sure those are all sorted. So 0, 0, 2, 2, 3, 3. After step 1, you basically sort it in the tens position. So now 0, 9, 1, 1, 7, so on and so forth. We notice how the order is preserved. 300 came before 90 because 300 was first in the original list. So in this case, we know that radix sort is stable. So we sort by the tens position. So here we go. If there's no tens position, we just use the number 0. And next we're gonna finally sort the tenths position. And again, if there's no hundreds position, we just place it at 0. And then we sort it. Ta-da! Okay, so radix sort, notice how it's like really good for like sorting huge numbers. So let's say you wanted to sort your UINs. Radix sort would be a great sorting algorithm for that one. It's just like huge numbers such as this, where it has like a lot of like let's say it's like 10 to the 6th power. Like you want to sort numbers that are 10 to the 6th power, like your UINs. As you can see, radix sort would be an excellent choice for that. Any questions? Okay. Wonderful. Is everyone good so far? Anything that does not make sense to them? Okay. No one seems to have any questions. So the next one. Oh. The next one I'm gonna go over is big O, because a lot of people wanted that too. So Nihar, if you're here.
Yeah, sure. So do you have like a specific type of question you all want to ask me, or I can also go over the examples from the slide if you want to.
Oh, can you? Oh wait, give me a moment. Someone's asking about stable versus unstable. So stable sorting will basically, like, let's say you have this one. Oh, here. Let me share my screen again. Oh yeah, don't worry about this tab. Let's say you have like one, you're sorting this 1 1 1 1 1, right? And for some, this is like, for simplicity's sake, I will call this A, B, C, D, E, F. So let's assume this is 1, and I'm just gonna call it 1A, 1B, 1C, 1D, 1E, and F. And in stable sorting, if you were to stably sort that, in the end, when you get inevitably 1 1 1 1, it should still be like 1A, 1B, 1C, 1D, 1E, F. Notice how like the order was kind of preserved. We weren't mixing up any ones. Versus in an unstable way, you would have something like 1B is now there, 1E is now there, F, A, B, C. So do you notice how like these ones, even though they were the exact same number, they were kind of switched around? Is that clear to everyone with stable versus unstable?
Yeah, I think this one can kind of be confusing because you're like, bro, they're all just ones.
Yeah.
Like, how can it even be different? But when you think about it as an object, right? Because all of these ones are objects that hold the value of 1, if it's an integer, I guess. You should think that it's the objects that are going to remain in the same order that they were before the sort, right? So if above stable is the original sort, those objects, object A, B, C, they might have the same value, but they're different objects. And if they remain that order after they're sorted, it's a stable sort.
Is this clear to everyone now? That was a great explanation. Okay. Someone DM'd me and said it was great. So yes.
Right. So let's now get into like bigger questions. Does anyone have? Oh, okay. How to find running time function? Wait. I guess there's one question about stable sort. Is stable sort important for the speed of sorting? So if you're doing if you're basically sorting in a list of numbers unstably, then you'll basically be switching the positions of numbers which you don't need to. So I guess in that way, or in that sense, you can basically say that the speed of sorting does change. But the main important point here is that when you're like doing something like radix sort, if you're not using stable sort in that case, then you'll end up with not the correct answer, because like once you sort one particular, for example, one digit and then tens and then hundreds or something like that, then in that case, you'll end up with, yeah, okay. I guess you guys already answered that question. All right. So the next question is how to find running time functions. Yeah, so I guess the answer for this is that it really depends on what kind of algorithm you're like working on, or like what kind of basically I guess for loops or while loops you're looking at. So for example, let me pull up my slides so that I can show you an example. All right. Yeah, is my screen visible to you all?
Yeah, we can see it.
Okay, cool. All right. So for example, in the first example, the way we find running time functions, the first thing we always do when finding running time functions is that we basically try to find the pattern in the iteration variable. So for example, in this case, the iteration variable is basically I, right? And so basically first is 0, and then it goes to 1, it becomes 1. So you basically need to check the increment and the bound. So it goes from 0, 1, 2, all the way up to n minus 1. And note that when you're starting counting from 0, the number of iterations is n and not n minus 1. So basically, whenever you're trying to find running time functions, if you look at all of these examples, what I first did is I always start with basically writing out the pattern or trying to understand the pattern in the iteration variable. So in this case, again, I goes from 0 to n minus 1, and then j goes from 0 to m minus 1. And so basically, again, in this case, the inner for loop basically iterates m times, and the outer for loop iterates n times. And so that's basically how we end up with 2mn for the count plus plus over here. So basically, count plus plus is again 2 operations and not 1, because you're first incrementing count by 1 and then assigning that value back to the variable count. And so yeah, I guess, does that answer your question? All right.
Hey, Nihar, could you go over like if statements? Seems like people kind of aren't sure if those count
Yeah,
when you're
sure.
making a runtime
Yeah,
function.
yeah. Right. So this is basically an example where we have like if-else statement. So basically, whenever you're finding Lego notations, we're always talking about like the worst case. So in this case, for example, there's if n%2 is equal to 0, then we'll go ahead and basically run this loop, which basically takes log n time. You can see, because we're basically multiplying the iteration variable by 2 in every iteration. So basically, in this case, I guess runtime functions are, I don't even know if they are defined, because in this case, I guess it's more important to know how to find like big O notation in this case, because runtime functions are usually meant to be or usually defined in general for questions where you know for sure, or there's just one path. So in this case, you could have like multiple cases. So I guess in this case, the more important part is to basically know that whenever we're finding the big O notation, we're looking at the worst case and not at some other like optimal case, I guess. Does that answer your question? Here?
Yeah, I think you
Oh,
should just assume Oh, sorry.
Yeah, so I guess there's some confusion about big of log n. What this over here means, this doesn't mean that a if statement takes big of log n. What I was trying to say over here is that this for loop over here, that for loop runs in big of log n time complexity.
Yeah, I think it's
So
fair to assume the if statement runs. And so because we assume the if statement runs, we're going to look inside the if statement. And what we see in this example is that it's a for loop and the conditions make that O of log n. So we can call the if statement an O of log n operation because of what's inside of it, right? If it's like a constant, like if it just said count plus plus, the runtime would just be 2 because count plus 1 is the addition operation, and then count equals count plus 1 is the assignment operation. So that if statement would just be O of 1 had it been just a count plus plus. But we're looking at what's inside of the if statement.
yeah, I guess that's a better way to like put it. Yeah, thank you, Andrew. Okay, just running the if statement, add to the number of operations. Yeah, so if statement is basically considered as like I guess 1 and then 2. So you're basically first finding the modulus and then checking if it's equal to 0 or not. So it is definitely considered to be like 2 conditions, I guess. But then when you're, so you don't count any other conditions for else statements, like you just do it once.
Okay, so there's like a lot of confusion with the O of log n. So when we're counting the overall runtime, we just simplified the if statement to be an O of log n, the entirety of the if statement. And the reason we call the if statement O of log n, it's because inside of that if statement, the for loop runs log n times. But the if statement we can explain to require O of log n operations.
Yeah, I guess a better way to put this slide would be to just like put it this in the next line, so that because what I'm trying to convey over here is that O of log n is the time complexity of the for loop over here. And then big of n is again the time complexity of the for loop in this bracket, basically.
Nihar, can you go over the other example where you had like the log, you know, where the answer was log? Because I think people are just confused on like
Yeah.
the times equals 2. I think that example
Yeah,
would help.
sure. Yeah, so basically, wait, check. Yeah, so this is basically the first example of log. Okay, so in this example, for example, we've basically been given a variable n, and we don't need to worry about the number of operations. I mean, that are basically this is zero operations, and then we start counting the number of operations from here. And so so while n is greater than 0, okay, so basically we basically iterate through the while loop, and for every iteration we're basically dividing the value of n by 5. And so okay, so the number of iterations in this case, so the way you find the number of iterations is by taking some examples of values of n. So and okay, so the way you decide which examples to consider is that we'll first try to take an example where n is basically a actual power of 5. So in this case, n is equal to 25, which is 5 squared. So that's basically why I took 25, and then I took 26 because it's basically not an actual power of 5. And at the same time, it's also pretty close to 25, so it's easy for me to like compare the formula. So basically, when n is equal to 25, after the first iteration, we basically have n will get divided by 5, and so n becomes 5, and then after the second iteration, n will become 1, and after the third iteration, n becomes 0. And when n is equal to 0, this condition basically doesn't hold true anymore. So we'll basically break the loop and exit the program. So basically we noticed that when n is equal to 25, there are 3 iterations of the while loop. Now, when we took n equals to 26, for the first iteration, n is again equal to 26, but then you divide 26 by 5, and note that this is integer division. So we basically don't consider the remainders and stuff. So basically 26 divided by 5 in this case gives us just 5 and not 5.2 or something like that. So 26 divided by 5 gives you 5. And then after the second iteration, we get n is equal to 1. And then after the third iteration, we'll get n is equal to 0, which basically doesn't hold true for, or basically the condition doesn't hold true. So we basically exit the while loop. And so again, we get 3 iterations. And basically there's, okay, so we have 2 options, like either it could be the lower function of log n base 5 or the ceiling function. So if you basically look at this problem, 25 and 26 basically have the same number of iterations. So that's where I got the lower function from. So for example, if you for example get that n equals to 24 and n equals to 25 have the same iterations, then we would have concluded that we should be using, I guess, the ceiling function, because that makes more sense in that case. In this case, we know that the lower function of log n base 5 is same for 25 as well as 26. So that's basically where I get log n base 5 from. And then +1 is basically setting the offset. So for n equals to 5 squared, we're getting 3 iterations. For n equals to 5 to the third power, which is 125, we'll again get 4 iterations. So basically I'm adding 1 to basically account for the offset of 1. And I guess I actually just realized something, that I actually forgot to count the number of operations I do for here, which is, okay, so basically whenever you're checking this condition and it's greater than 0, you're also doing one operation, right? Which is n greater than 0 or not. And if you think about it, the number of times you do this operation is going to be equal to, it's actually going to be 1 plus the number of iterations, because when you're doing the condition check the last time, you'll basically not iterate through the loop, but you'll still check the condition. So I guess the actual answer in this case should be slightly different. So will I add this term over here again? Does that make sense?
Okay.
And then we'll add.
Let me just clarify some things, like in regards to the test. A lot of you guys are wondering, oh, if it's in the if statement, does it count? Okay, if it's in an if statement, it does count. You do have to count it. So if it's like, if x modulus 2 equals 3, you know? The tricky thing about runtime functions, which I think a lot of you guys may be getting confused on, is that runtime functions, it's more of an art. And what I mean, not everyone counts everything as an operation. Not everyone agrees what should be an operation. So for example, not everyone agrees that assignments should count as an operation. And that's fine. It doesn't make it wrong, because at the end of the day, the purpose of the runtime function is to get the big O. Like, that's literally the only purpose of the runtime function. What I will say with this in regards to the test, if it's in a multiple choice, it will be very clear. We won't try to trick you with, like, it won't be like n squared plus n plus 1 versus n squared plus n plus 2. No. We'll have kind of very different runtime functions, from my understanding. In regards to your free response questions, with, like, in your first free response question, well, you have to do the big O of the code you implemented. And the second free response question, which will have to do with big O, be clear on what you count as an operation. All we ask is for you to stay consistent. So if you do not consider an assignment as an operation, just be sure to mention that. I am not counting assignments as operations. Some things that are kind of always counted are kind of like comparisons. Comparisons are usually counted. Any increments, so any arithmetic is usually counted. But again, as long as you are clear in what you're counting versus what you're clear when you're counting, you state that and you stay consistent, you will get full credit. And now it makes sense, like with like the for loops, for example. Like you can count that as an operation depending on how you're defining your operations. Sometimes some people don't even like count a for loop as an operation, which is fine, I think, but just as long as state your assumptions is all I'm going to say, because TAs are grading this. It's not auto graded, so you have some leeway.
A way that y'all can kind of think about if statements inside like loops is there's a potential for the if statement to actually never impact anything, right? Like, let's say you're doing like for I equals 0, I less than 10, and your if statement, it says, if I is greater than 10, do this. That if statement is never going to run.
Yeah, that's true. But the condition is always checked though.
Yeah, so that's kind of be like one operation. So it gets checked like n times. So the stuff inside of it does not matter as much as y'all think it does.
You always assume the if statement runs if there's a case for it. So like just because there's an if statement, that doesn't mean it's gonna run. Like, for example, if we go back to the, Nihar, can you go back to the example that you had with the if else statement?
Yeah, sure.
So in this if else statement, like you don't count the if and the else. You just count the if because you know you're guaranteed that only one of them is gonna run. Let's say you had like if n equals 0, and each time you're just incrementing n. Or sorry, let's say you have a for loop. You start at n equals 0 and you increment all the way to n. And let's say your if statement is if n is less than 0. That if statement is never gonna run, so you don't consider that for your big O, because there is no case where that will ever run. What you need to do with your if statements is you check the condition and you're like, in the worst possible condition, will this ever run? Does that make sense, Jeffrey?
Yeah, if I could make a point about this, I think someone had a question earlier about why it is still log n even though we're multiplying now. So right here we have our for loop. The for I equals 1, I less than n, I times equals 2. That's going to be log n because the end condition is I less than n. And you can test this if you just like say like I equals 16 or I equals 8. If we start at 1, we get 1, then 2, then 4, then 8, and then it won't run. And we can test that that's log because so we know it's going to run 4 times for n equals 8, right? Or 3 times because it's not going to run at 8. Log base 2 of 8 is 3. So we can see in that case, this is a log of n loop, but it really just depends on the end condition. Like the other, could you go to example 4, Nihar?
Yeah, sure.
This one is the end condition isn't while I is less than n. It's while n is greater than 0. So n, the value is actually decreasing, right? So our n value is decreasing, but if we were to plug in n equals 8 for this, it would still be log base 2 of 8, which is 3 comparisons. Because we do 8. Oh wait, no, this is log base. Is this log base of 5? Oh, I wasn't paying attention. But if this were n divide equals 2, it would still be log base 2 of n. I guess you could plug in the uses 26 for this example, but it's just the end condition of the loop.
For the question, is the running time for the if block versus the else block? You check the if block and O of n time and check the else block O of n, and whichever one's worse, you go for that one.
Okay, so basically in this example, if it was something like if n is say greater than 0, or greater than equal to 0, then in this case, this else statement basically runs only when n is less than 0, right? Because if n is greater than or equal to 0, then it will basically go in this branch of the program. And so if the program goes to else, that means that n is less than 0. So in this case, even though this for loop is big O of n, but this is never going to run because int I equals to 0 and I is less than n. So 0 is never going to be less than some negative number. So basically this loop will basically never run. So in that case, our answer would be big O of log n, because that's the worst case possible. Does that make sense?
Yeah, I think the runtime, I guess Navi said, what is the running time? I think the runtime for this, think of this as one big thing. We're trying to find the runtime function for this if n%2 or modulo 2 equals 0. This entire big loop or whatever, the overall complexity in terms of runtime is going to be, well, if you count, the count plus plus is 2 operations. That's 2 log n plus 1. So the overall thing would be, the runtime would be 2 of log n plus 1. The plus 1 comes from the if n%2 equals 0. And the 2 log n comes from the count plus plus happening log n times. So, and the reason it's not going to be like that plus O of n from the bottom loop is because, as Nihar said, we're going to assume that this bottom loop isn't even going to happen, right? We're just going to assume that the top loop is just going to go through. Oh, wait, yeah. Nihar, it says O of n to the right. Why are you considering the overall complexity O of n? Like over to the
Yeah.
right, you have big O notation.
Oh, that's because he changed the if statement. He
I
had
changed
n
the
less
if-
than 0.
That's
Originally,
like
it
a
was
different
n
case.
modulus 2 equals 0.
Okay, I see.
Yeah. So in this case, basically, if it goes to the else block, the only reason, the only case when, I'm talking about this particular code right now. So basically, if n is greater than or equal to 0, then we'll run the for loop over here. But if n is less than 0, then we go to the else block where we again have a for loop. But note that we are initializing I to 0 and then running this for loop while I is less than n. But if we already know that n is less than 0, then 0 is never going to be less than a negative number. And so in that case, basically this whole loop will never run. So there's no case whatsoever when this particular for loop will run. So in this case, the worst case is where n is greater than or equal to 0. And so thus we'll basically run this for loop, and so it will basically become big O of log n in this case. But if the question is something like this, where both of the loops are possible. So in this case, for example, n could be, for example, an odd number, and in that case, we would again run this loop. And so, for example, if n is equal to say 11, then in that case, the time complexity of this algorithm would become big O of n. So that's why the answer for this question is big O of n.
Yeah, in conclusion, just look for the overall worst case, but make sure that your if else statement, like that one of them will actually run. Oh, do we do the same for the running time function? Yes, we do the same for the running time function. In this case, like the original example of n modulus 2 equals 0, you will do you'll check the if statement, and then you'll do plus the running time function of the else block. So it'll be plus 1 plus running time function of the else block. Or should I say 2 plus the running time function of the else block, where 2 is modulus 2 and then equals. But you still take overall, you just take the worst case path, basically. Do we have +1 for int count equals 0. Do we have another +1 for count equals 0? Again, Navia, that depends on how you define operations. Some people do count them, some people don't. Do we count? Return statements are another one of those things that you just gotta like define yourself. In example A, oh, this is okay. Andrew's got Mia, I think. Okay, perfect. Any other questions?
What is tomorrow's quiz going to be about?
Tomorrow's quiz? Probably
Mhm.
ask. I have no idea.
I think it says something for tomorrow's quiz, but I just don't really have an idea what it's about.
Yeah. I
In
don't
the assignment
either.
it says do something about stacks and quickly.
Yeah, I'm not gonna lie to you, Jared. I do not know. I do not keep up with what quizzes you guys have. So I do not
Sometimes
know.
it'll say the date on the like quiz, like it'll say due at a certain time. That may be, so whatever quiz it says due like the 13th or something, that might be the one you're taking, but I don't think we really know exactly. Like if you just talked about stacks and queues or you just talked about something, I mean, I think it's fair to assume that that one might be coming up soon, but
It says it's postfix, stacks and quiz and stacks, but we had a quiz on Friday, so that's why I'm trying to ask.
oh, like do you have quizzes on exam week?
It's tomorrow, I think. It's due on February 14th.
Yeah, like Jared, we do not know.
It's fine.
Sorry about that. Okay. So I'm gonna send out another Google form because I feel like you guys are a bit shy. So here, if you would like, you can ask your any other questions you have in privacy. You do not want to tell the world. Oh, Andrew. Yeah, Andrew wants Thierry to go. Oh, it's more about not knowing to ask, what to ask. Can you explain the purpose? Ah. Nihar, do you want to take this one? What do you mean by like a lower versus upper bound?
So
Oh, Nihar's got it.
so I'm assuming that you're talking about big O, big theta, and big omega, I guess. Is that what you mean? Okay, yeah. So basically, the main purpose of I actually explained the reason for tight bounds over here on one of these sites. So whenever we're trying to find big O or big theta or like big omega, what we're trying to do is basically compare two or more like algorithms. And so in order to do that, we need to know how fast or how slow an algorithm is in its best or worst case, right? So sometimes there's some cases when you always know that the algorithm is going to run on. So for example, if you're sorting a list of say integers, and somehow you already know that most of the numbers are going to be, for example, sorted, then it's like a good case, right? For like sorting, so that like in that case, you probably would like to use an algorithm which works better in like the best case, versus in some other case, you already know that it's always going to be like really bad or badly shuffled data, or sometimes it could be the other way around. So I guess the main reason we learn like upper and lower bounds and basically try to like classify algorithms into like different big on notation categories is to compare different algorithms and understand which one is the best algorithm to use.
Okay, someone I think
I think someone said they wanted stacks and queues.
okay, wait, give me a moment before we move on to stacking queues, which we can totally do. Someone asked what the point of stable was if you want to sort. So I think that comes from a misunderstanding of stable sorting. I gave the example of like, let's say you had 1, 1, 1, 1, 1, and obviously it's kind of like useless to sort that. But let's say you had 5, 2, 1, 1, 3, 2, right? If like there's 2 1s just in the middle, you don't want to switch those places necessarily.
Well,
Alright,
okay,
this
do you
is
want
a-
me to stop sharing my screen so that you can?
Yeah, you can
Sorry.
if you would like.
Okay.
Do we need to know auxiliary space? Mia, what do you mean by auxiliary space? Anyway. Okay, here we go. Here's another example of stable. If we have 1, 2, 2, 6, 2, 3, 9. Right, this isn't sorted. So again, let's assume this 2 is A and this is like 2B. When we finally sort this 2, 2, 3, 5, 6, 9, yes. We want these 2 A's for it to be sorted. We want these 2 A's to preserve its position so that it's A and B as well. And versus if this was unstable, these 2's will have switched positions to be an A. And again, it just has things to do with like, if there's no need to swap them, why would you swap them? Like that just takes more time, more effort, more memory usage. So it's just better, like if they're already the same like number, if they're equal to each other, don't bother swapping. Does that make sense to whoever asked the question? So stable's algorithm not swap 1, 2. Yeah, basically. That's right, Jared. Okay. Let's go. Who had the amortized runtime? That has something to do with stacks and queues, no?
I see. I think so. I think
Oh my
so.
goodness, it's your time to shine.
Finally, I've been waiting for so long. I'm joking, but yeah, there is some sort of amortized analysis and stacking queues. So I will finally share my screen. All right, hold up. Do y'all see this?
Yes.
All right, perfect. All right, so since there's already a convenient video being made, it's only 8 minutes long. Great video length. I can still briefly go over like what a stacking queue is and basically possibly just highlight like what you should like emphasize on for the test. So put the slideshow on. Do you also see it?
Yeah.
Or okay, perfect. So for what a stack is basically it follows a abstract data structure that follows a LIFO policy. So last in, first out. And there's 3 basic operations, which are push, pop, and top. And push and pop, all that happens at the top of the stack. So that's basically these operations you gotta need to know how to use a stack. So if you're still confused on how that works, I made a beautiful example right here where if you have access to these slides, you just go over and like follow the example here. Like for example, there's a list of operations on the side right here, and for each operation, it's going to show how it works. So when we push 5 into the stack, Mr. White's truck, which is a stack truck, is going to show 5 being pushed into the stack, and for these subsequent operations, it's going to show how it works. So when we push 9, hold up. When we push 9, you see 5 and 9 on top of the stack. And how it was described in chat too, it's similar to how like a stack of plates work, where when you stack one plate on top of the other and you want to remove a plate, you can't just remove the middle plate. It doesn't make sense. So you remove the top plate first every single time, or you add a plate on top. Let me pull up chat real quick to see. All right, beautiful comments. So yeah, so if you're just confused on how like a stack works, I'll just go over the example right here and just like see how it works. And if you're still confused, just go over the video itself. And one like tip I would do when you're like, studying for the quiz is you can actually like, if you want, possibly make a copy of this slide and create your own example. You can create your own like values right here, create your own operations and see it work out and play like step by step. And that's personally how I learned like stacks and queues personally. And I think the most important part about the stack abstract data type is, let me just get through all this stuff. There we go. Is that for the worst case amortized analysis, you're going to be analyzing the push and pop operations. And we see that for the worst case, it's O of N. And the reason why the worst case is O of N is that there could be a scenario when the stack is full. And then if you want to increase the capacity to stack, you have to copy the values of the old array to a new array. And that takes O of N times. It's you have to go through every single existing value and put it into a newer, bigger, array. And we see here that this worst case doesn't really happen like every single time. Like for example, when you stack dishes, you're not gonna, let's say like the dishes are stored in like a vertical container. You're not gonna like every time you add a plate, you're not gonna add a bigger container like every single time. Like it doesn't make sense. In the same way where you're not gonna create a bigger array every single time. Since in this case, we double the capacity. That's why. So in the average case, we see that over a large number of operations, once again, we don't see the worst case scenario occurring every single time. So that in this case, we can apply an amortized analysis and over push like operations. And we can see that, on average, the push operation takes O of 1 time or constant time. And then for the pop operation, it takes O of 1. And that simply just takes the element off the top of the stack. There's nothing, it's pretty straightforward, honestly. So that's what the stacks are. And next, we have queues. And queues have FIFO policy, or first in, first out. And there's 3 basic operations, quite similar to stacks, but the policy is different right here. First in, first out once again. There's an NQ, DQ, and front operation. And they're both insert, delete, and view. And this basically inserts into the front of queue. This basically deletes from the front of the queue. Oh, sorry. This inserts from the back of the queue. Sorry. This enqueues to the back of the queue, like a line. Similar, and we'll see that in the example. DQ deletes from the back of the line, or from the front of the line. And front is, it peaks the front of the queue, essentially. Sorry for the confusion. We'll see a better visualization in the next slide right here. And we have here Mike Ehrmanhott from a very good show that you also watch, look it up. And we have a good queue example. Once again, I'm not going to go through the animation one by one. I think it'll take too long. But as you see visually, when we push elements into the queue, they're essentially following a line. And when we push more elements, they're like following line by line. For example, in this scenario, it's like cars lining up for a parking ticket booth. They're lining up line by line in order of which one came, So that when we pop, or like let's say like when the pop operation comes, it pops from the front of the queue. And that's basically how a queue works. And I explained this more in my video. I'm basically just trying to go through a quick rundowns of how it works. And once again, you can also like tinker with this and make your own examples and see just drag and drop. And that's a great way of understanding the general logistics of the queue itself. And once again, for the worst case and amortized analysis of the queue, we see that for NQ, the worst case is also O of N. And it's a bit similar to how we see the worst case of stack is that when the queue is full, in order to increase capacity, we have to copy old values and put the values into an array of a bigger capacity. And that takes, once again, O of N times, since you have to copy these values. And once again, we see that this worst case scenario or situation doesn't happen every single time. And once again, we can apply amortized analysis and a big emphasis on other push-like operations. We can apply and see what the average case is over like, a sequence of operations. And we say that most of the time, when you're adding an element to the back of the queue, it only takes O1 and once again, constant time. And for DQ, once again, worst case is O1, you just take the element from the front of the queue. And yeah, that's it. And this next topic right here, let me take a quick breather. This is a big one right here. It's possibly going to be in your exam. I would personally put a big emphasis when I took this class, circular queues is what I would say will cause a bit of confusion with a lot of students. So I would make sure if there's one thing to take away, look at circular queues and see how it works. And the motivation for circular queues is that for a regular queue, we see in this past example that in situations where the queue is full, you're going to be able to have to adjust for a bigger capacity when the queue is full. And so the good thing about circular queues is that the circular queue avoids having to occasionally make space in the array for a new element by reusing and recycling memory. In this case, in our last example right here, as we progress through here, you're noticing why can't we just use these recycled space? Why can't we recycle these spaces and reuse them later in the queue so we don't have to extend the capacity of the array over time? And that's basically the motivation for circular queue. You're basically going to be reusing and recycling, memory by reusing indices in the array itself. So there's a front and back variable for circular queues where the push variable increases the push operation increases the back variable and the pop operation increases the front variable, where back starts at capacity -1 and front starts at 0. And I'm not going to go through the full example right here because it's quite long, but what I would say here is that I'll go over the first few operations. So for a circular queue, we see that, once again, the front starts at 0 and the back starts at capacity -1. And when we push, 3 into the circular queue, you can see like a normal queue, it inserts it to the front of the queue itself, or the element into the front of the queue itself. But we see that since we push something into the queue, will we have to code circular queues? I don't think so. Is that right, Sophia? You don't have to code circular
No,
queues?
absolutely not.
Yeah, no.
But
I'll just say
you
that.
do
Yeah.
have to do examples like what we're doing right now, like push
Yeah.
3, push 9, pop, push 4, like that. That is on the test.
Mhm.
So
Yeah, which is why I would put big emphasis on going through these animations and examples and just seeing how it works. Because I feel like where you have a question where it says here, where are the values of front and back after, you're probably going to see that in your exam. You might see that. So it's important. It's a good question of this example question is a good way of seeing whether someone actually understands how circular queues work after. So I would go through this example right here and follow the operation as it goes. So as you can see, there's an animation that I've created, which goes through step by step how it works. And it will follow what the instructions are in this green highlighted part are, essentially. I don't want to reiterate myself. I feel like it's self-explanatory to see in an 8-minute video. So I'm going to skip to the main points you take out of this is that it's a great way to reuse and recycle memory. And it uses, front and back variables. Yeah. And compared to a regular queue, we see that the worst case for NQ is now going to be constant time, since we're reusing recycling memory by using the same array. And for DQ, the worst case is constant time, so we don't have to apply amortized analysis here because the worst case doesn't really pop up every now and then like for normal queue itself. So a question here is, so you can't make circular queues bigger. I'm not. Can someone answer that? I kind of.
okay.
I'm not sure about that. Yeah.
So technically you can, but basically if you're making a circular queue, you're not supposed to.
Yeah.
Obviously it's possible, but the point of the circular queue, you're basically stuck with that size.
So with a regular queue, you aren't allowed to shift items once you pop stuff. We can go back to that. For a regular queue, you notice that like, you know, in a circular queue, at a certain point, let's say like when you, perfect example right here. So let's say like the circular queue like set up like this, whereas you have like 4, 5, and 12. Let's say you wanted to push 83. And then like a normal like queue, you wouldn't be able to put this element like where it is right now at the, you know, at the beginning of the array again. You're gonna have to create like new space. But with a circular queue, you're able to utilize the module operator and create a circle effect in which future values will be able to be, you know, placed in the beginning of the array, like a circle, essentially. Is that correct? I'm not sure if I explained that right.
Y'all kind of need to think of a queue as a literal line. That if
Yeah,
you're standing in
yeah.
line for something, like someone coming in front of you is unfair, or you turning to your friend and saying, let's swap places. You can't do that. Like you're stuck in the position that you're in. You can only
Yeah.
go to the back and wait for your turn.
Yeah, that's a great way of explaining it. A great way. But why can't you shift the last 3 forward and then add it? Which part? Which example? Oh, in the regular queue, why can't you shift the last 3 forward and then add it? Oh, like these values? Like the 24 and 23? Oh, yeah, basically, yeah, you can't really shift it. Let's say like let's decide that right here. It's like that's a capacity of 5, right? If you want to, you can't really shift it because like if you want to shift 20, 24, and 23, 23 can go to the last element, 24 can be in the second to last spot. But if you want to like add more like values, you're gonna have to create a new array of a bigger capacity, essentially. So you can't really yeah.
Oh, go for it.
Wait, go ahead. Yeah, sorry.
Oh no, I think notice how these queues and stacks we're implementing with them with array. Queues and stacks, like the actual definition is like first in, first out versus last in, first out. So you don't necessarily have to implement it as an array. We are right here, but like let's say we have a linked list. So I think the confusion, why can't you shift the last 3 forward and then add it? Like you can, but just think of this, we're in an array. We don't want to actually copy the values. It kind of like in this example, having a queue kind of seems useless because of all the wasted space, but it's kind of because the implementation we're using is with an array and it's kind of harder to do queues with an array. But in the future, you'll see that you can implement queues like with the linked list. And in that case, it'll become much more useful.
Yeah, great. Yeah, that's a great way to explain it. Thank you, Sophia. I would say, yeah, you're kind of constrained to what type of like how you implement your queues in, essentially. So let's say if you use a better data structure for this, and yeah, I think you're going to be able to, it'll be more efficient with a better data structure instead of having to double the capacity of an array every single time you want to, you know, add more elements. So yeah. Sir, any more questions? Let's see. Let me scroll up. Is that it? I think that's it. Yeah. But yeah, main takeaways, I'm going to do like a quick TLDR. Look through these examples. These are very helpful in understanding how it works. My 2 cents would be to like make your own examples and go through step by step. That's personally how I learned. You gotta like take the time to like absorb the information and also look at YouTube videos. You know, those are free. There's so many like visualizations. There's also like Google, like certain websites that actually do the operations for you, and that's like also a good example. And yeah, are these going to be posted on Canvas? I think it's already in the document right here. I think, is that posted on Canvas, this document?
I don't think I sent out an announcement. I did forget to post the document. Can you just link that document again to the?
Yeah,
and I'll have everyone like, you can also find this document if you go to the playlist. It's in the description of the playlist. I did comment on every one of them with the link to the playlist, but I think YouTube thought I was like promoting something because I definitely did comment that, and I looked back and it wasn't there anymore. So here it is.
Yep. All right. I think, is there any more questions regarding stacks and queues? Okay, I think, is that it? Yeah. I'll stop sharing my screen if no one has questions about it.
Mm,
Oh, all right. Real quick. Yeah.
Go
no
for
worries.
it. Go, go, go.
Yeah, no worries, Jeffrey. Yeah. Is the value of front and back capacity minus, wait, is the value for front and back? Oh, and 0 for front, yes. Wait, the value of, yeah, it starts out, yeah. The back variable, when you first set up the circular queue, it's set to capacity -1, which is basically like, you know how your array works, like, 0 to 4, essentially capacity -1. And then front starts at 0, which is the start of the array itself. Yeah, that's correct. Yeah, no worries. Yeah, honestly, when I was, if I'm being honest, I was like, making these slides myself. I had to relearn a lot of stuff, so it's good to ask these questions. All right, any more questions?
Okay,
All
if
right.
y'all have,
Oh, what is the value when the circular queue is? Oh, okay.
Oh.
Oh, sorry. What is the value when the circular queue is full? If I'm not mistaken, isn't there a count variable implemented with the circular queue? I think it's, oh, yeah, when it's full. Isn't this it? I'm not
Wait,
sure.
I don't know. I don't understand what you mean by the value. Like, do you mean what the front and back are
Yeah.
pointing to?
Yeah.
The front and back, I think, will just be pointing. Well, actually, you can take this.
Yeah. I think, yeah, we see here that when back equals front, that definitely means that it's like, there's only one entry within the queue itself. But whenever it's full, I honestly am not sure.
They're gonna be right by each
Yeah.
other. So if you like, can you go back to your animation to
Yeah.
like when it's fullest? No, 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 no.
Is that it?
Yeah, notice right now,
Yeah.
if the array was full, if you think of it logically, you'll see that
Oh,
the
yeah,
back will be
yeah.
all the way to index 1. Does that make sense, Mia? Perfect.
Yeah.
Please. Oh, today is Super Bowl. Oh, I forgot about that.
Indeed is. Yeah, you kind of notice a certain tab here, so. All right. Is
Oh.
that the rest of the questions
What
regarding
does it mean
stacking?
pop increases fronts?
Oh, yeah. When pop, what it means by pop increases front, pop means, I think a better way of saying it is NQ, because this is for queues. So whenever you put something inside the queue, you're gonna increment that front variable, essentially, or move the front variable by 1 within the, like, where it is in the array. So let's say the front is like at, index 3, right?
Mhm.
Or, it's a better way of showing it in an example. I think it's a lot better. So
Okay.
yeah, so let's say we push 3 into the circular queue, right?
Mhm.
We'll put 3 in the front of the queue.
Mhm.
Oh, sorry, it's the pop. Let's go to the pop operation. Sorry. So let's say we have a scenario where we have 3 and not, we push 3 and 9 into the queue, and the next operation is a pop or a DQ. So when we DQ, we remove 3 from the queue and we move front by 1 to the next index, which is 1.
Oh, I see. Okay.
Yeah. Yeah, and once again, you see how we're front, in that example right there, at that instance, front and back, we're at the same spot. That's basically also what it means when it's a 1 entry queue.
Oh, but what about the regular quickly? Does pop does the same thing?
Yeah.
Or
Yeah,
not
with
for-
with the regular queue, I think, yeah, the front still moves, but we don't have like that back variable we keep track of. Yeah. You don't keep track of a back variable. In the
So it's
regular
not
queue.
different apparently.
Wait, it's not different?
Yeah, like I see what pop doesn't behave differently.
Yeah. Wait, what do you mean? I'm confused.
Like pop in the normal quickly does not behave differently than pop in the circular quickly.
Yeah, pop takes pop. Oh, sorry. Pop in the regular queue, takes from the queue, and
Mhm.
same way pop takes from the front of the queue in the circular queue.
Yeah, pop
Okay.
acts exactly the same way in both.
Yeah.
What kind of
You just
what
have this
acts different
additional
is push.
operation. Yeah. Yeah, that. Sorry.
Okay, I see.
That's like if you were to like see it in code, you're just gonna have like additional like operation where you do increase the front variable.
If anyone has any other questions, we can either go over comparison based algorithms really quickly, but like there's a video on that, so you can watch that instead. Or we can finish early, or we can see what questions anyone else has. Oh, you're welcome. If you enjoyed this format, please let us know, because if this was not useful to you guys, there is no point in doing it. If you like the videos, please tell Dr. Lake, because this is kind of a new thing we're doing. And if Dr. Lake does not know that this is helping you guys, it will be cut. So, just mention that.
I think we may even release videos a little bit earlier so they can kind of digest the information better and have specific questions, but not super early because then we have to do the
Yes.
work faster.
That might be for future posterity. It will be released earlier, but for you guys, maybe not. Yes, again, please let Dr. Lake know if you like this format. Okay. Well. Oh, well, the recording of this review. The recording will be just added to the playlist.
Good luck, y'all.
Yes. Yes, you can stay if you had questions with your homework. Oh, we're having homework questions now. I wonder if these 26 remaining people are at their computers. Let me see. Let me check. Not again.
Okay, so I'm looking at the problem right now.
Oh, thank you,
And-
Erin.
Yeah, no, all good. It looks like what was said in the chat, essentially you want to rewrite this code as a templated version. If you go on to our, I think it's either week 1 or week 2 slides from class, we have an example